I just want to share with you today this notion about putting Java inside of a container. There's been some difficulties with it in the past, and there are some interesting things that have evolved over the last couple months, last 2 years, and have been interesting in the Java space that makes it more friendly to be running in a container. And I want to share some of those with you today. We're going to be walking through a couple of these points that I have on the screen here. Distilling containers. I'm going to talk about this idea of a distillation. It's a distillation pattern. We're going to talk about Java and the challenges of getting Java inside of a container. We're going to talk about containers themselves. A little bit about CI/CD, not much, but the majority of this is going to be showing you a hands-on example that you can run by yourself. And I'm going to show you this hands-on example using a platform I use all the time. It's called Kata Coda. So I'm going to show you a Kata Coda session where we're going to take Java, put it inside of a container. And what we're going to do is we're going to start with a very large, fat container, and we're going to squeeze as much water out of it as we can. I'm going to squeeze that water out of the rock. And at the end, I hope you'll be impressed about how much water we can actually squeeze out of that rock and get and still maintain a working application. So this is me, Jonathan Johnson. Let's see if I can get on to the next slide. This is me, Jonathan Johnson. I do lots of speaking. I'm an independent consultant. And I do a lot of speaking around the cloud native system, lots on Kubernetes. And obviously, containers is a big part of cloud native and Kubernetes, and getting those containers just right is very important. So I do like to cover a lot of the topics that are around this, and this is one of the ones I get pretty excited about because having efficient containers inside of a larger system such as Kubernetes has a direct impact on money cost. The fatter your containers are, the more resources you're going to have to spend with your cloud vendor. The smaller you can get those containers, the more distilled they are, the more you're going to save in terms of money. Now, I know I usually do surveys. We don't have enough time to survey, but I would say probably 50 to 75% of you, if not more, have already experimented with putting your applications in containers. And many of you probably are already running in production with your applications in containers. There's a wide variety that here online, and there's some people that, you're at this talk and you just haven't put your applications in containers yet. That's fine as well. I just want to say there's a wide range. More and more people now are getting more comfortable getting applications to be running packaged and running in containers. And beyond that is not only running them in containers, is run multiple applications in multiple containers and then tying them all together. And that's when I get into my Kubernetes talks. So there's idea of like the language you use, and then there's also the languages that you'd like to use. Now there has been a large amount of people in corporate and in large applications and large companies, large products, tend to use Java in the enterprise as well as C#. Python has made great strides in terms of people also using Python in terms of containers. But there's other languages that are vying for our attention, that are coming after us, and we're all thinking about different types of applications, the different types of languages that we want to put inside of containers to write our applications with. Containers are polyglot, so it's a lot easier to start thinking about different ways of putting your application into a container using different languages. So you might be allured by other languages like Go, or even something maybe lightweight like Node.js, or doing something more interesting, more performant like Rust. And then you have flavors of Java like Kotlin. All of these things you can put in containers, and the question is, which one can you do? No longer, or I should say, we're moving toward ideas where our development shops are no longer have to be one language, one version, because you as a developer, as infrastructure as code, because you're putting things into a container, you're more in control of that container. Therefore, you're more in control of the stack of things you decide to put in that container, which can be not only Java, but different versions of Java. Now, I know most of you are probably, quote unquote, stuck on Java 8. but because you're running, if you are running in containers, you have more of the freedom, the liberty to move to newer versions of Java without affecting your company. Because not everybody has to be on the same language when you're running in containers. There's this article by George Schad, also co-written by Ken Sipe, who's a speaker on the GIDS tour. And they wrote this article back in 2017-18, which was a long time ago, essentially, before COVID. BC. The 2017-2018, they wrote this article basically saying there are problems running Java in container because of memory and isolation problems. Now, they've been fixed since this article came out, but basically their feedback was don't run Java in container. And now that's changed a lot. Java has improved tremendously. And I'm going to get into that in a few minutes when I talk about the Java aspect of running Java in containers. But first I want to talk about the distillation pattern first. So the distillation pattern, call it PDOPS, reducing things down to the most essence of the best of what you, the essence of, when I'm talking about whiskey, in terms of boiling down something into the best essence of flavor. And the idea about putting your applications to containers is that you want high cohesion and low coupling. Now, what I mean by that, I'm going to get into a slide where it talks about the different aspects of the distillation pattern. And I'm going to take you through, in the hands-on, I'm going to take you through the distillation, a couple of different techniques for distillation using Java, hopefully to squeeze that water out of the rock, the container. So the distillation pattern I see is there's 8 factors related to it. And what I'm seeing in the industry is that a lot of people are talking about a lot of different things around containers. And the focus tends to be on these 8 factors. It's the 8 factors of reducing that container down as much as possible. And I don't mean just the size. There's lots of things that you can do to reduce. And here are the 8. So the 2 high ones, the most important ones, I see a recurring theme, and this goes back to my computer science 101 days back in college. High cohesion and low coupling. We do this object-oriented programming all the time. High cohesion means all the things that you're inside of your class, like go back to your class and your object-oriented programming. Everything that's inside that class should be there for a reason. Your methods, your private members. If you have extra import statements that are not being used, your IDE will show them gray. Take those out. If you have extra methods in there that are no longer being called, take those out. If you have a set of methods in your class that are really part of a subclass, or they really should be taken out, refactored into another class, then those should be put into a different place. That's called high cohesion. You're taking things out of that application, or out of that class, or out of that package, or out of that container, or out of that jar file that no longer are relevant to that package or to that bounds that you're talking about. That's a refactoring we do all the time. That refactoring you do in object-oriented programming in your classes is the same refactoring you would do inside of containers. Take out the things in that container you don't need if they're not relevant. Dependencies. Do you have a bunch of dependencies in your container that you just don't need? Take them out. Low coupling is along the same idea. Let's go back to the class again. Say you have a bunch of API methods in your class, and some of those methods are public, but nobody ever calls them. Or you do call those methods, but they're only called privately, and your static coding application or static scanners such as SonarQube may warn you saying, hey, you've got public methods in here, you probably want to make them private because the only thing that it's calling these methods is something within that class. So that's called low coupling. In other words, reducing your API. That also applies to REST APIs, making sure that the things that you're exposing in your REST API is versioned and you're purposely doing it. You're not just throwing on a whole bunch of endpoints without testing it and then really understanding what your customers need your REST API for. So, and that's really important. It's all about reduction and making sure that your container, your application is doing one thing and does one thing well, whatever that one thing may be. And I'm talking in the land of microservices, in that form of wrapping our microservice inside of a container and making it highly cohesive and low coupled. So two other ones are immutability and idempotency. And usually immutability is all about the idea of when the container runs, you don't want it to be changing and morphing at runtime. Why? Mainly because it's difficult to debug it and really to understand the nature of that application when it's running in a container and when it's running on Kubernetes inside of a pod. If something goes wrong with that container, that application in the container, and over time that application has changed, mutated, it's very, very difficult to understand what happened and what's going on in that container. So we always strive for immutability within containers, within our microservices, or running on larger platforms like Kubernetes. That's really important. So that's also part of the distillation and making sure things don't change over time. I can go into lots of examples there, but I hope you understand. I don't want to spend too much time on that. Idempotency. The best way to break idempotency, what is idempotency? Idempotency is the ability to run something each time, and every time it runs, it always runs the same. What's the best way to break idempotency? I usually do a survey and ask you, but the best way to break it is latest. You ever do a version of a jar file or of a container and not put the version on there or put :latest? That is actually an anti-pattern. It's an anti-pattern in DevOps, because you're now, every time you build that artifact, you're pulling down the latest dependency. And that latest dependency may have a breaking change in it. So that means every time you do a build and you run your application, it may not run the same. Therefore, you're breaking idempotency. So idempotency is really, really important. And that's also part of the distillation. Understanding exactly your dependencies. So you've refactored your application to make sure the only things in your container are the dependencies, the only dependencies in there are the ones you actually needed. But to go that further, the only dependencies you need are specifically versioned so that they're idempotent over time. It's really important. Another one is attack phobic. That is very much related to low coupling, but attack phobicus is talking about reducing the attack vector, not allowing people to get into, say, your container and mess around with it. For instance, if you allow somebody to shell into your container, can they get into something like apt-get or yum or some kind of a package manager inside the container? And can they copy in new files into the container? And are they running in your container, when they shell into it, are they running as root? These are all attack vectors. These are all different ways that somebody can come in and actually mutate your container in different ways. The more they can do that, the more you're exposing yourself to security issues. The more you're going to fail security audits or some kind of a security scan. There's a security scanner for containers called Claire. It's an open source security scanner. And it will find things like that where you have vulnerable attack vectors within your container. So small images, one of the things we're going to be concentrating on the Kata Coda session that we're going to do in a few minutes is small images. There's many different types of distillations that we can do, but a lot of people actually tend to focus on small images, and it is important. If you have a small image, it tends to build faster, not all the time. Sometimes it takes extra work to build that container to make it smaller. But once that container is built, the smaller it is, the faster it can be transported up to a registry, and the faster it can be pulled from a registry and started on, say, a Kubernetes node and spun up. That speed and efficiency, and the less bytes that actually have to be transmitted over the wire, will actually save you money. It will save you time, cost, and money. It adds up. If you get into the hundreds, if not thousands of containers, that's a significant number that can really add up. So you really want to make your image as small as possible. Rapid startup is another one. I'm going to be talking about rapid startup. When your application is in a container, you want that container to start really quickly, right? That's important, and we're going to talk about that with Java inside of a container, because Java notoriously has been slow to start because it has to load all these classes into the JRE and the JVM. There's also resource frugality, meaning when you're running your application, you also have to think about how much CPU and how much memory. You know, what does Kubernetes do as an application or as a platform or as a framework? I don't know, whatever you want to call it. In many ways, what I call it an operating system. It's an operating system for your data center. It's an operating system for cloud. You know, cloud 2.0 data operating system. That's what Kubernetes is. And what does an operating system do? It manages CPU, memory, and I/O. Inside your container, you are a consumer of CPU, memory, and I/O. So you need to tell the operating system how much you need, because you're not one container for the entire application. You're one of dozens, hundreds, thousands of containers. They're all vying for those precious resources, CPU, memory, and I/O across multiple nodes in your distributed system. So it's very important you tell Kubernetes, hey, I'm this big, or I'm this big, or I'm this big, so it knows where to put your application. It's called bin packing. It's one of the scheduler does within Kubernetes. So you want to tell Kubernetes and other container runtime engines exactly how much CPU and memory you need. These are the 8 factors related to distilling your container down. Often people talk about making your container image small, but there's many things. Attack vectors, how much CPU, memory, and I/O you're using, startup speed. You get it, you understand? This is the distillation pattern, and we're going to be attacking the distillation pattern with Java. So in Java, whenever you make a choice of Java inside of a container, right after that, if you're going to be doing something like microservices, then you have to choose like a microservice framework, and then you're going down the route of, do I do REST? Do I do gRPC? Do I do GraphQL? There's different protocols you can put in there. That framework, that REST framework that you put inside of it, makes it interesting with Java, because there's lots of different frameworks, Java frameworks to choose from. But before I get into the frameworks, I just want to talk about, I'm not going to talk about the history of Java or anything like that. But I do want to show you that, you know, we're in a 6-month cadence with Java, if you don't know that. Every September, every March, we have a new release. There's one that's coming up, Java 15. So Java 8 is out, and a lot of people are, like I said before, we're kind of stuck on Java 8, but Java 9, Java 10, Java 11, there's been a lot of advancements to Java over time, and new features have been added. Many of those features, actually, I was just peeking in on David Delabassi's session just before mine, and he was talking also about the idea of, like, as Java has moved along since Java 8, it's done more to make Java friendly to be running inside of containers. And I want to echo that same notion that there have been lots of things that have to happen within Java that made it better. Now, remember that article with Kensight and the other fellow? That article was talking about an early version of Java 8 that didn't run well in the container. And here's what the problem was in a summary. When you ran an application inside of Java in the JRE, and the JRE was inside of the container, what would happen is the application, the container would normally get a slice of memory. And that slice of memory from the host operating system was what is available to the container. There was a defect, essentially, within the JRE that when it looked at the memory of the computer, it would actually didn't see the memory of the container, it saw the memory of the whole computer, of the whole host. So what happens when you run that Java application is, if you don't give it any parameters, it will take, by default, a quarter of the heap. So when you ran Java in a container, it was taking a quarter of the heap of the entire node, rather than a quarter of the heap of what was available inside the container. So the application and the JRE actually thought it had a lot more memory than it actually did. So it would run, and then sometimes it would hit a ceiling, and it would actually crash pretty horribly. thinking that it had more memory than it actually did. And the container boundaries actually put a limit on it. It's like, no, you can't have that memory, and your application would crash. So they recognized this back in Java 10, and they realized it was so important that they backported that patch back to Java 8.191. So if you're using Java inside of a container and you're stuck with Java 8, make sure you're using update 191 or later, which came out, can't remember the date on that, but it came out about a year and a half ago. There's been other advances that have been added to Java. There was an interesting one called JLink. We'll talk about that in a second. There's another notion called ahead of time compilation. We've heard about just-in-time compilation. Well, there's another one called ahead of time compilation. There's a new type of runtime engine rather than hotspot. It's called GraalVM, and there's some really interesting advancements that's being promoted by Oracle. So there's a lot of advancements with GraalVM. OpenJDK came into space, and there's some. Look at this one. In JEP 320, they removed the old Java EE and the Corba modules. So that's the distillation pattern as well. They're taking out things that are no longer relevant or being used or should be deprecated. They also rewrote the transportation layer. Well, that makes sense because we're putting a lot of microservices in containers, and what are we doing? We're making SSL calls and to our containers. So rewrite that. In Java 13, they rewrote. They re-implemented the legacy socket API. So these are all things related to, hey, we need to do more things with Java to make sure that runs really well in containers, specifically with microservices, and Spring Boot is pushing a lot of that. Many other, I don't want to go into the details of all the other JEPs that have been added to it, but we're coming on, there's other garbage collectors, other algorithms for Java collectors coming out, non-volatile memory. A lot of things are coming out. So I do want to cover one thing related to a significant thing that we're going to be looking at is called JLink. And JLink, when I first thought about it, or when I first saw it, I was like, what is JLink? JLink, oh, it actually will compile your application? It'll link your application? No, it doesn't do that. What it does is Project Jigsaw, modularization of Java. If you provided a JLink, your classes, or a jar file or a WAR file, if you provide JLink that, it will look at all the things that you're importing, you're using, and it will look at all your dependencies. And if it finds it or you're not using significant modules within Java, for instance, if you never do anything with SQL or JDBC within your application, and it doesn't see any dependencies on JDBC, JLink will create a new JRE for you without those modules inside of it. That's part of the distillation pattern, right? So it's not compiling your application, it remakes a new image of your JRE. So now you have a distilled JRE just for your application, and you can load that inside of a container. It's one way to reduce the size of your container. And then, of course, there's lots of frameworks out there. The elephant in the room, of course, is Spring Boot. Most people tend to use Spring Boot these days. And there's other ones. There's Vertex, Dropwizard. There's a few other ways, choices. As a Java developer, if I want to put, say, a microservice in a container, you can use Spring and things like that. And they typically tend to be things related to REST and sometimes gRPC, or some kind of an endpoint that you want to have stand up your microservice on. And then I put the special ones in a box. The special ones are Micronaut, Quarkus, and Helidon. Those three are related to GraalVM. Those are frameworks that are like Spring Boot, but rather than at runtime, dependencies are being injected and discovered and introspected. They're determined at compile time. And that determination at compile time really helps GraalVM to efficiently do things like ahead of time compilation and faster startups. So wouldn't it be nice? You imagine runners. Imagine when your application runs, wouldn't it be nice if when your application ran, it started right away? And that's exactly what app class data sharing does. So when your class needs to be loaded in the JRE, it has to go through these steps. Look up the class in the disk, load the class, verify the code, and then put that whole loading of the class structure into a data structure in the JRE. What app class data sharing does is it preloads that data structure and writes it as a binary as part of your executable, or as part of a table that, so when your application runs, all the classes are actually preloaded for you and pre-validated. That doesn't work well when you have dynamic class loading and introspection of your classes and dynamic class loading at runtime. But it does work well when you do it with statically understood classes that you're using within your application. You have your startup time for your application becomes much faster when you can leverage a Java runtime engine that understands app class data sharing. New feature that was added after Java 8, forget which, I had it in my timeline. But once, I think it's Java 10. So once you have that, your startup time decreases significantly, 20 to 50%. There's another one called ahead of time compilation. So just-in-time compilation is as the application is running, the JRE figures out optimal ways to optimize things, and it compiles things binary as it runs, and it makes it more efficient. But it can't do that for all the code that during your startup of your application. It can't do all that. So there's this idea at compile time to figure out, we want to pre-compile the startup time of the application so that it starts up faster. It's another thing that was added, and Java 9 experimental, and is now part of the JRE. So GraalVM is taking advantage of these. In fact, GraalVM is an implementer of the CDS and AOT. That's why it's exciting. Helidon, Micronaut, and Helidon, Micronaut, and Quarkus are the three that take advantage of the GraalVM. Now, the one I'm really interested in, I'm going to show you in a few minutes, is the linker. You can actually, there's this thing called native image, and it's an executable, and it actually will take your application, and if it knows all the classes up front, it can compile a binary. And if you think about it, distillation pattern, this is the big part of this talk. A container runtime engine, and what Docker files are all about, it's package once, run anywhere, right? We, for years with Java, it's been write once, run anywhere. So we have a JRE that can run anywhere. We can write our class file, it runs anywhere. But now we have containers that we can package, and if I built my container on Windows, I can run that on a Linux machine, or I can run it on an EC2 on Amazon. So I can package once, run anywhere. So why do I need a JRE that runs anywhere? I just need a JRE to run inside of my container, and I know what my container is. It's going to be an Alpine container. It's going to be a Debian container. I know the operating system I'm in, so why do I need to run anywhere? I just need to run on that Linux. So in many ways, that pattern, we're violating the distillation pattern by having both a runtime engine for Docker and a runtime engine for Java. It doesn't make sense. So compile if we know what we're going to be putting our application into, compile it to that binary. Use native image to take your Java application, build a binary out of it, and put it on Alpine or put it on Debian. Okay, that's the notion of it. And I want to get to it quickly because we're running out of time. I don't want the demonstration takes a little bit of time, but I want to let you know this is coming right from the website related to GraalVM. When your application is compiled with GraalVM and run with a GraalVM, it's not 50% faster, it's 50 times faster in terms of the startup time. So that old notion of like it takes, Java takes a long time to start up, no longer containers. And that's really significant with containers when you have lots of containers spinning up and spinning down, and you get more into like things like functions, like Java functions running inside of containers. You want those containers to spin up very quickly. And now you can do it with GraalVM. You also have a significant reduction in terms of memory footprint, not 5% better, but 5 times better. And there's better garbage collectors. The GraalVM has its own version of garbage collection. So this whole thing is not about a talk about GraalVM and the specifics of it. There's lots to learn about GraalVM, but I just want to let you know that's something you probably want to look into. And there's 3 frameworks out there. If you're used to Spring Boot, pretty easy to transition over either the Quarkus. There's another command line tool called Piccolo, which also is another framework that takes advantage of GraalVM for writing command line tools. Because when you write a command line tool, you want it to sort of start up fast as well. I don't want to spend too much time on it. I'm just doing a time check here. 6:30, 6:30 my time. So we got about half an hour left, and I do want to get on to the hands-on. I do want to say just really briefly, I put the slides in the chat window, so go ahead and if you missed that, but it's in the chat window. So I'm going to be skipping over some of these slides here because I don't have enough time. But I want to let you know that a lot of Java applications will have some base containers. When you put Java inside of a container, there's all of the idea of like what do I do, from Debian or from Alpine? And there's that choice is all based upon the C library that's inside of the container. The C library is the library that your JRE is linked to in order to make calls to the kernel, the Linux kernel, which is on the host machine. So that's an important library to be linking with. And that's the standard C library. And there's 2 choices. There's MuselC, which is Alpine, which is very lightweight in terms of, it makes your container much smaller, but it's not always as compatible and as feature-rich as the GNU C library is that you often find in Debian containers, which tend to be heavier and fatter. So a lot of people like Alpine, but there has been historically in the lack of distributions of Java that are supporting Alpine. And the OpenJDK kept kicking that can down the road for a long time. And for a while, there was a gap there where you just couldn't get a OpenJDK binary that was compiled for Alpine because of the MuselC testing that needed to be happening. So there were other projects that came along, like Adopt OpenJDK. They supported both Alpine and Debian and MuselC and the GNU C. There's Portala, another project that was supporting it, and another commercial system, Azul Systems, that is also fully supporting different flavors, especially Alpine. So, some people say, you don't want to be using some Java in Alpine. Well, there are ways of running Java in Alpine, and now with later versions of Java, the Alpine versions are available again with the OpenJDK. Dockerfile is very straightforward. If you haven't looked at it yet, it's about 17 commands. It's very nice to put together to package your applications. Here's 2 lines of code that will put a website inside of a container. 2 lines of code, you got a website. 4 lines of code, you have a database. 4 lines of code, you have a Spring Boot microservice running in a container. I'm oversimplifying a bit. There's a few more things you may want to put inside your container, but this is the minimal that you could do. And there's a OpenJDK JRE Alpine, and you can run a Spring Boot application inside of that. Is it distilled and following the 8 points, the distillation pattern? No, it's not, but it will work, and you can chip away at it. Another major thing that happened with Docker, with Docker 17, was the idea of multi-stage builds, and we're going to get into that in a second. I'm skipping over that quickly because I want to get on to the hands-on learning. There's a couple other tools related to shrinking your application. One's called Dive, which is really interesting. You can either use it as interactively or you can use it in your pipeline. And Dive will look inside your container and reduce it down to, and help you reduce some of those dependencies and pull out some of those dependencies in the layers you don't want to use. So definitely look into Dive. There's another one called Docker Slim that will take a large container and slim it down. It'll look at the things you don't need in the container and take them out automatically. And you get some good reduction with that. But we're going to going through a slimming down exercise ourselves. I just want to let you know, a Docker file or an OCI container, Open Container Initiative container, is just a tar of tars. Each layer is a tar file. And here's an example of just a slide takeaway for you to look inside your container to see how it's built. I'm going really fast here because I don't want to run out of time for our demonstration. And okay, so container registries, I'm going to show you an example of that in a second. And also, there's lots of ideas about security scanning. I want to call out two that are highlighted there in yellow. One is Claire for doing security scans, but another one's called Falco, which is security scans and other types of scanning at runtime. So sysdig auditing tool is really cool. So that scanning is all related to distillation as well. So we're going to get on to the Kata code example, and I want to spin it up very quickly so that we have it up and running. So I've written a lot of Kata codas, which are scenarios that are teaching ideas. I have a bunch of courses on them related to Kubernetes, Kubernetes fundamentals, Kubernetes and containers, running serverless. I have a course on chaos. I do lots of different talks and lots of different coverage on cloud native and things all related to Kubernetes. This is one of them. So I've written a course under containers for Kubernetes, and one of the scenarios in that course is distilling Java containers. So that's what we're going to run right now. And hopefully we'll get done in 20 minutes. All right, so this is just the introduction page. I'm going to skip it. If you hit that little, sorry, that's being clipped right there. What you have at your beck and call right here is on the left-hand side are the scenario instructions. And on the right-hand side is a Bash shell terminal that's starting up. It should just take a second to start. It's running kind of slow. So I'm going to cheat a little bit. I'm going to spin up another container, another Kata Coda instance, and see if that one goes a little bit faster. Because sometimes I get a slow server. This is all free, by the way. There's no credit card. You can run them by yourself at any time. All right. Well, we have a container. We have one up and running. So, we have a Kubernetes cluster at our beck and call, and we're going to be running all this on Kubernetes. Do you need to use Kubernetes for this demonstration? No, you don't, because what we're going to be doing is just building a container. But I do like to leverage it a little bit just to show you how things work. And that is really running very slow. Let me go to my other instance here, and that's still spinning up. So we might have a little problem with speed, which will have an impact on us completing this scenario. But we'll give it a try. The old try. So we have, the first thing I want to do on Kubernetes is I want to put a container registry on it. And once I have a container registry, I will know, you know what I'm going to do? I'm going to start another session over here just in case. Hopefully that one will be faster. 3 times the charm, right? See, it's taking a long time. This command should have taken, I don't know, 3 seconds, 2 seconds to run, and it's hung right now. So it's telling me that I'm going to be in trouble here. Now, this one seems to be running a little bit faster, so I may abandon the first one and go to the second one. I'm sorry this is so confusing. I basically have 2 Kata Coda sessions. That's interesting. This one's faster, and if I do that same repo add, it should come back very quickly. and it's not. There it comes. All right. Well, this one is definitely quicker. So I'm gonna commit to this one over here, or the second one. So what I'm doing right now is I'm just adding to Kubernetes a private container registry, because we're going to be building a Java container, and I want to be able to build that container and then push it to Kubernetes. Sorry, I want to push it to this registry. So that registry just installs into the kube system namespace, and in a second it's available. So this is a good I have a good instance here, and if I curl against that registry, it should be running in a second. So sorry, kubectl get in the names, get pods, make sure it's all running. It is all running. That curl command, oh, I didn't run the registry, that's what it was. So that curl command, now, okay, there it is. So, sorry, I'm just going a little fast here. Right now, we now have a registry, and I just did a curl command against its catalog, and it's showing me that I have no containers in the registry. So let's take care of that. So there's also a web interface for it. We'll install that. The first thing I want to do is just want to pull down a sample Java application. It's a Spring Boot application, so I'm going to do a git clone. And inside of it, it's a standard Spring Boot application. Here's your directory structure. And it's built, I used just Spring Boot initializer, and then I chose Gradle. So there's a Gradle run that will run this application. All this application does is it looks at the current directory, and it counts up all the files and the size of the files inside them. It's called lister. So it lists the directory recursively and tells you all the files. So I have 56 files here, and then just the application just ran. If I build it into a jar file, there's my jar file. And if I look into build libs lister, sorry, it's cut off at the bottom. Lister, there it is. Maybe you want me to zoom in a little bit. That might help. Yes. All right. So nothing crazy so far. Nothing to do with containers. I just want to show you we have an application that's built with Spring Boot, and it runs, and we got a little bit of timing here. So it takes about 192 milliseconds to run this application. Natively on this terminal, this is a uname-a. This is a Linux box. Okay, happens to be also our master node for Kubernetes, but it's just a Linux box. We're running Java. Okay, so we're going to put it into a container first, and we have just a stupid fat Docker file that Docker JRE Slim, and takes the jar file and runs it. You know, drop the mic. That's a very basic way of putting Java jar Spring Boot application in a container. So let's build that container and see how big it is. All right, we're not looking at security and all those other distillation factors, just focusing on the size of the image as one of the distillation factors. And in a moment, yeah, so there we have it. And if we do a Docker images, we find that the size of it is 184 megabytes. Now, it could be worse. I've seen containers a lot larger than that, but I also know that it's pretty fat, and we can make it smaller. We can distill this much more. And by the way, this is not a very large Spring Boot application. It doesn't have a lot of dependencies, so there's no really justification for that being that big. So if we push it to the registry, it's going to take a while to do it. And this is an example of when you have a large container, it's going to impact things like transporting it to the registry. So you saw how that took a few seconds to do. So now if we say Docker run, and we run the application to walk the directories. Now, the directories are a little bit different. In fact, there's many more files here. So it took a little bit longer to run, but it significantly went up. It took about 3.5 seconds to run versus less than 200 milliseconds the last time. So we've actually gone in the wrong direction. By taking our Java application and putting it inside of a container, we've significantly slowed down our application. I just ran it again, a little caching, and it went a little bit faster, but it's still about 3 seconds. So what can we do about this? All right, let's figure out what we can do. Let's get it into an Alpine container. Alpine, as you know, the base Alpine image is about 5.5 megabytes versus we've got a larger Docker Slim container, which is based on Debian, and that is about 150 megabytes, I believe, something like that. I forget. But it's larger, much significantly larger. So let's take our same Docker file and instead change the from to just Alpine. And let's build it. And once it's built, we're going to look at the size of it. Whew. And we're done. It's hard to tell. I get this. Yeah, I've got this thing here. There. All right. So now we've got built. Let's see how big it is. Now it's built. So we went from 184 megabytes just by switching to Alpine. We removed 100 megabytes just by switching the base operating system that's inside of it. That's significant. Every time you do that, the question is, will my application still run? Let's try it. So let's push it to the registry. Let's see how much faster it is to push to the registry. Hopefully you'll see that I didn't put a timer on it, but it is faster, a bit, about 100 megabytes faster. And if we, so we just push to the registry. And if we look at the size of this container, sorry, we just ran it. So we just ran it. Are we running any faster with Alpine? Sorry, let me just, no, it's actually running a little bit slower even. Now you got a little bit of variance there in terms of running it. 3.5 seconds, 3.5 seconds. So whether it's Debian or Alpine, the runtime is still about the same. But it is, we did one thing related to the distillation pattern. We didn't make it run faster, but we certainly reduced the image size, and we still get an application that runs and it does its same work. So, okay, well, Alpine is buying me something. So let's get into multi-stage containers. So multi-stage container would be something like, rather than doing my build in Gradle, let me do my build in Gradle inside a layer, one layer in my, not a layer, it's not a Docker container layer, it's a stage. So let me build my jar file in one stage and then copy it to another one. Now, you're not getting a lot of the significant advantages with this. You usually see Docker builds like this when it gets to compiling. So in Go, you don't want to have a whole bunch of things. If you have a basic Go application and you want to build a Go binary, the last thing you want to be doing is shipping inside your container all of the Go binaries to build Go. You just want to have the Go binary of your application in there. So often what people will do is built in the stages before this stage, see there's multiple froms? In the first from is when you'll be doing the actual compilation. And the reason is because you want to do compilation that's native to the container that you're targeting, or the operating system in the container that you're targeting. In this case, we want to be building toward either Musil-C or GNU-C. But we still have the JRE, so it really doesn't give us a non-significant advantage. But let's just build it. We have a multi-stage container. We're building the jar file inside the container. And my question to you is this container going to be smaller, the same size, or larger than the last one we did? We're still using Alpine, but we're now building the jar file rather than externally. We're doing it as a pre-stage to the final stage of the Docker file. What it's done is it has increased our build time. And you're going to find that sometimes when you start getting into things like multi-stage Docker files, is that your build time for building these containers is slower or longer, but it will, there are advantages when you start getting into compiling binary. And, you know, spoiler alert, we talked about native image, and we're going to do a native image with our Java, and we're going to be doing that in the stage. So we just built that container. And the question is it smaller, larger, or bigger? So we went from 184 megabytes, and we switched to Alpine and went to 84 megabytes. And then we did multi-stage, still the same size. And that's not a surprise because we're not really doing anything in that stage except building a jar file, which we had already done before. But I just want to introduce the concept of we have a multi-stage container. We can push that to the registry as well, much faster because some of those layers are already cached. And now that we can run the application, and it's still going to take about the same amount of time to run. All right, so still basically it's slow. All right, so now let's get into JLink. Remember when I talked about JLink? It doesn't compile your application, but it reduces the JRE for your needs. And this is just an application that's going over a list of directories. So a directory list. So there's not a lot of dependencies in there like JREs or JPC and SQL and many other things. So there is an opportunity to strip out. So let's run through. There's two utilities, one called JDEPS and one called JLink. JDEPS gives you a dependency. If you want to see what all your dependencies of your jar file are, just run JDEPS, name your jar file, and you'll see all the Java modules that it uses. And then that gives you an opportunity to run JLink to have it stripped down a new JRE. So JLink, this is the Docker file to take advantage of JLink. And we're going to do that multi-stage. So we're going to take there's Gradle W jar. There's one task to build a jar file, and there's one other one to do the JLink. And then we're going to take that binary that gets built into the build image directory, and that's going to be our new JRE inside the container. So rather than doing from Java, so we're just going to say from Alpine, and then we're going to load the JRE into it. But it's our JRE that's lighter weight. So the question, let's do that. I just have to make it a modular Java file there. So we're going to build the container, and it's going to significantly increase our build time because now we're not only just building our jar file, we actually have to build the whole JRE with JLink. JLink takes some time to process. So we're hitting our build pipeline kind of hard, but it's after the idea of, hey, can we squeeze more water out of this rock? We should be able to do it. Let me check the time. About 8 minutes. We'll see what we can do here, folks. If I can't get to everything, you can run this kata coda by yourself and take your time and read through all the instructions. And it's basically repeating what I'm trying to take it through very quickly for you, because I know you got many other sessions to get to today before the day ends. So let's look at, so we just compiled it. Let's look at the size. We went from 184 megabytes. We went to Alpine, 85 megabytes. Then we just did the JLink, and look at that. We stripped out another, what is that, 50 megabytes or 40 megabytes? Out of that, well, we cut it in half almost. So we're marching toward, that's a significant advantage. Now we have a much smaller container. So when we push that container to the registry, it pushes that fast, almost. All right, so it is faster. And will it still run? We've got a reduced container. Will it still run? Absolutely, it will still run. And is it any faster? No. All we're doing is we're stripping dependencies. That doesn't make it run any faster. And stripping dependencies just makes the image smaller. Yeah, you can inspect the image. I'm not going to get into that, but you can shell into the image and you can prove to yourself that indeed it has a reduced JRE inside of there. So let's get to the interesting part where we do native image. Let's see. See that? See this GNU? Here's our multi-stage container from Builder. And we're going to do, okay, so I cheated here. So I'm doing an Alpine container, but I had some problems running it with GNU, with MuselC. So I found somebody who took an Alpine container, and along with MuselC, they also put GNU-C in there. It's not that much larger, and it works. I do want to make the scenario. So I believe I can, my point is I think I can get more water out of the stone. But even with this, I think you could be surprised. So we're going to take our jar file, and then we're going to take our jar file that's already built, and we're going to put it inside of this. We're going to compile the jar, and we're going to take our binary, which gets built into this directory by Gradle, and we're going to put it into the container. So the only thing that's going to be in our container is our compiled Java binary, which is kind of weird. So we're going to do a Docker build. Now, I've just added a significant amount because essentially inside of that build, it's running JLink, but it's also doing the binary build of your Java application. And if you notice, I'm actually not doing it with a Quarkus or Helidon or Micronaut. I'm actually doing it with Spring Boot. And I said, well, you can't use GraalVM with Spring Boot, but I can in this case because I'm not using any dynamic class loading, so I can actually get away with it. But if I was going to do anything larger, I would switch over to one of the three. I'm not going to say which one I prefer. I just, there's three of them out there. They're all competing with each other. If you, I'm just trying to think what else I can give you before we end, and we're waiting for it to build. If I can summarize what was going on here, we have inside this container, inside the Docker file, we're building everything. We're building a binary using Java. We're getting rid of the problem of we have a package once run anywhere and a write once run anywhere, two architectures that are no longer competing with each other. So in our Docker file, we're saying, fine, we don't need to write once run anywhere. We need to write once, compile it, and then we can put it inside a container that can run anywhere. Is this container going to be smaller, larger, or the same size? Well, the point of this talk is smaller. So I think you can guess by how much smaller. I think you can guess it's going to be smaller, but hopefully I can surprise you with how much smaller it is with exactly 3 minutes left. I don't know if I can do this. And I'm at the mercy of the performance of this machine. But if we can't get there, I will reveal it to you. In fact, I know you probably want to go on to other sessions. We're going to let this run, but I'm going to do the reveal for you right now in the text. When it gets compiled, it will be down to 25 megabytes. All right, so there's the reveal. When you build this container, it'll still run. It is taking a lot longer time to build, but it's the container went from 184 megabytes, 65 down to 40 megabytes. Now we're down to we cut that 40 almost in half down to 25. I believe that I can squeeze some more water out of this by making it truly an Alpine image, not Alpine with GNU-C inside of it. See, it's still building. That it's stuck on the building step right, not stuck, but it's working on the building step right now of building our binary. And that's why it's on the screen like that. So can we have access to the sample? Yes, you can. I'm going to put it right here in the URL. Good question. Any questions, by the way? You can run this course at any time. If you're an O'Reilly subscriber, it's also on the O'Reilly Learning Platform, but the URL I just showed you is a public URL. Anybody can run it at any time, even in India, okay? It's fine. And there's no credit card, no sign up or anything like that. It's free. It gives you an hour. It's an instance that's running for an hour. And sometimes they don't run as fast and sometimes they're kind of slow, but it's free. Hey, you can't complain. So it's still running. And I'm going to just continue here. And if you need to go off onto other sessions, I'll just pop out to my slides. If anybody needs to contact me or ask questions about this, feel free. There's another on the slide takeaways, which I will too. Here's my slide takeaways. You can look at my slides at any time. Okay, And I just want to let you know, if anybody needs to contact me at any time, I'm an independent architect and independent consultant. I do lots of training, mentoring, teaching, especially around these topics. So you can reach me at any time. If you have any questions on this scenario, feel free to reach out to me through any social media contact. And I really appreciate you attending this. And I'm disappointed that it's still compiling. But believe me, it will compile in a few minutes, and it would be running and reduced container. So thank you all for coming, and enjoy the rest of the tour, the rest of GIDS.